talk a little bit about organic chemistry, and organic chemistry is the study of carbon-containing compounds. So that's pretty much the first sentence in any organic book, is that it is a study of carbon and carbon-containing compound. Most organic compounds really have kind of a similar sort of backbone and sort of how they are connected. Really, most organic compounds are carbons basically attached to carbons, and attached to those carbons are hydrogens. And that is really sort of your basic organic sort of molecule. That carbon to carbon attachment, carbons attached to hydrogens. There are, as we'll talk a little bit about, different sort of functional groups in organic chemistry, and these different functional groups basically represent different types of organic molecules that you come across, and most of them result from basically substituting maybe some of these hydrogens for other elements like oxygen, nitrogen, maybe some halogens along the way. A couple of things about carbon, since it really is the makeup of all organic sort of molecules. Carbon, as you remember, hopefully has 4 valence electrons, I hope. And really important with carbon is it needs to have basically 4 bonds, right? So basically carbon wants 4 bonds. I should have really 4 bonds. That meets the octet rule for carbon. You should never go over 4 bonds. Sometimes when people start organic chemistry and start drawing them, they just keep laying on bonds on the carbon, and ends up with like 7, 8, and that type of bonds to it. So it should not go over, obviously, 4 bonds. It should not have more than 8. It is a N=2 second energy level element, which means it has no d orbitals, so it cannot do the expanded octet. That happens with the period below it at sulfur that can go past 8. So carbon should always have that 4 bonds. Now, in terms of carbon bond, that is going to be a nonpolar bond, as they will have the same electronegativity values. So that difference in electronegativity values would be 0. In terms of the other very popular bond that we have there is the carbon-hydrogen bond, and that also is a nonpolar bond. If you do the difference in electronegativity values, carbon's like 2.5, hydrogen's 2.1. That's like a 0.4 difference in electronegativity values. And if you remember from your lectures on Lewis structures and bonding, anywhere from a difference in electronegativity values of 0 to 0.4 is considered nonpolar, equal sharing of electrons, basically. No positive or negative sign to that bond. Anything above 0.4 to below 2 is considered a polar bond, right? Which means basically it's unequal sharing of electrons. The result of that is we will have a partially positive side of that bond, a partially negative side of that bond, where the negative side is the more electronegative atom in that case. And really, although you don't really need it, anything above 2 is typically ionic, not in all cases, but pretty much if you have a metal and non-metal, that's definitely going to be ionic. So that's really important there. When we talk about carbon and carbon really bonding to other carbons, it can make different types of bonds that are commonly seen in organic chemistry. We could have carbon-carbon single bonds, which are alkanes. That's the group of organic molecules that basically have carbon-carbon single bonds. We could have carbon-carbon double bonds, which are actually a group of molecules known as alkenes. We could also have carbon-carbon triple bond happening there, which are known as alkynes in organic chemistry. Other things that we typically will see carbon do in organic chemistry is it can double bond to an oxygen. It's a very common sort of bond. This is what is sometimes referred to as a carbonyl group. And that's a carbonyl carbon, where the carbon here is partially positive and the oxygen is partially negative. So these are very common sort of bonds that occur with carbon in organic molecules. In addition, we do get some hybridization, and think about hybridization. So if you remember when we talked about hybridization, perhaps in your first class that you took here, that is when we take some atomic orbitals like our S's or P's and our D's and we combo them together to make hybrid orbitals, like sp hybrid orbitals, sp2, sp3, sp3d, sp3d2. And really, these are combinations of these atomic orbitals like S's, P's, and D's, bring them to the same energy level. They have the same shape. It allows for better overlapping, and also the geometries that we see associated with some of these things. There is the electron pair geometry, which goes with these guys, and really you could count it like you do geometry. So if you remember, when you count electron pairs, when you're doing geometry, you count double bonds and triple bonds as single electron pairs and single bonds. So basically S and P is 2 letters. That's basically 2 electron pairs. So that is linear. sp2, that's like 3 letters. So 3 electron pairs is trigonal planar or triangular. sp3 is really 4 letters, and that's in 3 P's. So that's 4 electron pairs, which is tetrahedral. sp3d is 5 electron pairs. That's a little triangular bipyramidal. That is your expanded octet, 5 electron pairs. And this guy on the bottom there is basically 6 letters or 6 electron pairs, which is octahedral. That also means that in terms of the bond angles that we associate with these guys, and it does pop up occasionally as you go through some organic guys, we'll get some different geometries as we maybe make double bonds or triple bonds that occur there. So for example, if we had, something like this, put like them all in here, one molecule, why not do that, do that, do that, and do this. All right. So if we want to assign hybridization to these guys, this guy right here, this carbon has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4. Simplest way to do it is start at S, 1, 2, 3, and 4. That's an S and 3 P, so that is sp3 hybridized. Over here for this carbon, we would have 1 electron pair here, 2 electron pairs here. And again, this double bond would count as only 1 electron pair, which is 3. So that's 1, 2, and 3. So that is sp2 hybridized. If we look at this carbon right here, has 1 electron pair, 2 electron pairs. Once again, that double bond would only count as 1. That also would give us 1, 2, and 3, which is sp2. And lastly, kind of looking at these last couple of guys over here, we'll come here. Has 1 electron pair there. Again, the triple bond counts as 1 electron pair. That's basically 2. So that's an S and a P in terms of hybridization. And so would this guy be sp hybridized. So that's really the fast way that you could figure out hybridization of carbons, is basically count up the electron pairs. Again, you basically do it the exact same way as you do geometry. Double bonds or triple bonds, again, count as 1. Any questions on that? Also a reminder, since we're talking about this a little bit, we have, in terms of, say, hybridization, we'll look at, say, an sp guy here. When we take our S, actually, let's put some of that there. So if we're going to do a little sp hybridization and we look at carbon, for example, electron configuration 1s2, 2s2, 2p2, which is the 4 valence electrons that we have in carbon. And if we put those in, right, it'll look something like that. When it goes through hybridization, you might remember when these lower electrons get basically promoted up to a higher energy level. And then when we hybridize an S and a P, that means that we will end up with 2 sp hybrid orbitals, which each have an electron in it. And in this case, we'll actually end up with 2 unhybridized p orbitals. And that is where our double bond and triple bond comes from, is from those unhybridized p orbitals making sideways overlapping, also known as pi bonds, right? So these guys can make sigma bonds. So if you remember, a single bond is oftentimes sometimes referred to as a sigma bond. That's when the orbitals basically go right at each other and overlap. If you have a double bond, it's made up of a sigma bond and a pi bond, which is the unhybridized p orbitals doing sideways overlap. And if you have a triple bond, it is made up of a sigma bond and basically two pi bonds. And that's what we would have here. That would make one of the double bond, if you will, and that will make like your triple bond, the overlapping of those electrons do so. Any questions on that there? So when we talk about organic molecules, and really because it is made up primarily of carbons attached to carbon and carbons attached to hydrogens, and since those really are all non-polar sort of guys, that affects some of the properties that we see with normal sort of organic compounds. And because pretty much this guy is non-polar, it is going to want to use dispersion forces as its main sort of intermolecular force. And remember, intermolecular forces are the forces that one molecule uses to basically interact with another molecule, either itself or a different molecule. And all intermolecular forces basically are the basic connection of a positive and a negative guy together, basically coming together, and that's attraction that occurs. So in dispersion forces, which are relatively weak sort of intermolecular forces, that's why something that's organic like this has a little trouble with water, because water is polar, and water has this polar bond between the O and the H on both sides, and it wants to use hydrogen bonding. And a reminder that hydrogen bonding is a bond between hydrogen, nitrogen, oxygen, and fluorine. Needs to be there. So water wants to use hydrogen bonding. This organic guy wants to use basically dispersion forces. They pretty much don't mix because of that. There's no really long way that they can maintain those interactions, as this is a very strong intermolecular force, and that's pretty much your weakest sort of intermolecular force that you could have. So what usually happens, right, if you sort of mix these two together, is we will see separation of those two. For example, typically your organic guy is less dense and on the top, and your aqueous or water sort of part is on the bottom of those things when you mix them. So this is also why, for example, organic molecules typically have low melting points and boiling points, and that is because they're held together by these really weak dispersion forces. So if you think about some of the basic organic molecules that you probably are familiar with, things like methane, right, propane, butane, those are all gases pretty much, and that's because they're really held together by very weak intermolecular forces. It doesn't take a lot for them to basically go into the gas phase. So a lot of organic molecules are what are said to be volatile, which means they go into the gas phase very easily. That's why when you take organic chemistry, they throw you in a fume hood, and you can do all your experiments in the fume hood, because a lot of stuff that you use is very volatile, could go into the gas phase really well. A, you don't really want to smell it, and B, a lot of that stuff is also very flammable, which means you don't want it near any type of open flame. So usually they stick you in a fume hood, maybe you share with somebody, and you do your experiments. So with that being said, we can, though, see in other sort of organic molecules sort of changes in some of these properties. There are some organic molecules that can be very soluble in water. So, for example, if we were to replace one of those, say, hydrogens in either of these guys and replace it with an OH group, what this would then do is turn really this organic guy into a different type of organic molecule, and this would be an alcohol because it has that OH group, and that's the functional group of an alcohol. That OH group is really the same group that you see in water. It is partially negative on the oxygen, is partially positive there on the hydrogen. It still has a second part of it that's really nonpolar, but it does have that spot right there, which is polar. And that actually gives something like ethanol, which is what this guy is, to be fairly soluble in water, because again, they are able to do some hydrogen bonding to each other through those type of things. So, depending on sort of what functional group that you have, you can have some organic molecules that are pretty soluble in water and able to hydrogen bond depending on what's there, especially things that have an OH group. There are things like carboxylic acids, which have this group, which basically has a negative and a positive carboxylic acid. And that is a positive and a negative as well. So these guys also very soluble in water. Now, because they are soluble in water and they're still organic, there is a limit to the solubility, and you do start to see a very big decrease in solubility with water when you build out sort of the nonpolar side. So if I were to add on a bunch more carbons and just hydrogens to that side of it, which is the nonpolar side, the solubility pretty much drops to nothing. So usually around 4 to 5-ish carbons in that ballpark, and sometimes 6. Once you start hitting that many carbons on an organic compound, even if they have that OH group, pretty much solubility goes down the toilet there, because basically for it to be soluble in water, it has to replace water and water interactions that are hydrogen bonding with themselves. Water is a relatively small molecule, and as you build out the sort of nonpolar part to these sort of guys, what you're doing is making something that's really big, and now it's not going to fit really well with water. And even when you build it out, it just has a small part over here, sometimes referred to as steric hindrance. Basically, the big nonpolar part gets in the way of water being able to get in there and interact with it. So you lose a lot of the solubility. So most things that do have the ability, for example, in organic chemistry to hydrogen bond, you have some fairly good solubility up to, like I said, about 4 or 5 or 6 carbons, depending on what it is. But then you definitely see it sort of fall off in terms of solubility. Any questions on that there? Now, in terms of boiling points, we also do see some changes in boiling points when we look at different organic molecules, depending on the functional group. So for the most part, alcohols, which are these guys here, pretty much have a really high boiling point because it has the ability to hydrogen bond with itself. This guy over here, which is an alkane, has a pretty low boiling point and melting point, because again, all it can really do is dispersion forces, and even with itself, it's not going to be very strong attraction, and that's going to allow it to go into the gas phase. Actually, this guy right here, the carboxylic acid, because it's actually able to hydrogen bond with itself in 2 places through the carbonyl carbon and also the OH group, it's actually has the highest boiling point, even higher than an alcohol. Alcohol could almost beat everybody, but carboxylic acid actually can beat alcohols in terms of boiling points because of that ability to sort of interact with itself there, and makes like a dimer when 2 of them get together, and you get all these hydrogen bonding between each other. Now, when we look at organic compounds, there are some different types of formulas that we very commonly see. So obviously we can have a molecular formula that we are probably used to. So like C3H8, and we can also have a formula where we sort of draw it out. So CH3, CH2, CH3. This is what is referred to as the condensed formula. You basically don't draw out the hydrogens, although it does appear the way this is written that the connections like between the carbon and the hydrogen, you should remember that is actually between the carbon, and the hydrogens are attached to the carbons. You can actually draw out the hydrogens, which is another type of formula that you see in organic chemistry. And it looks something like this, which is the expanded structural formula. And really the only difference basically between the previous one and this one is you draw out the hydrogen. So you basically show all the hydrogen. Probably in most cases, if you take a real organic class, unlike the fake ones, if you take a real organic class, line structure is typically, and I'll just draw a different one, is basically what oftentimes you will use. And this is usually sometimes referred to as line structure. And when you draw line structure, pretty much that's what it looks like. You really don't label anything on it. It's really a basic sort of structure. It doesn't get too crowded most of the time, but just to show you where everything is, pretty much wherever a line ends, if there's nothing put there, and anywhere lines come together, those are all carbons, basically. So those are all carbons all the way through there. And basically, as we talked about the importance of carbon having 4 bonds, everything else is assumed to be hydrogen in this case. So this guy at the end, which has 1 line coming in, would technically have 3 hydrogens. This guy right here has 2 lines, which means to get the 4, you need 2 hydrogens. Same thing with this guy. Same thing with this guy. And again, you don't usually draw any of this on a line structure. And this guy also would need the hydrogen. Guy at the end there would need 3. So again, basically just a line structure is kind of like a zigzag sort of up and down type of move. And if you see a line by itself, it is meant to be basically a carbon at the end of that, which would also have 3 hydrogen, which is known as a methyl group. So in a line structure, if you see a line with nothing at the end, it is that CH3. If you see in line structure a line and they want something there, they will actually write what it is, like BR or something like that, or OH and stuff like that. So line structure is very commonly used, and again, it illustrates some of the structure that we see. You could also double bond or triple bond there in a line structure. If you wanted to, you could throw in a double bond there, or you could, for example, make it a triple bond. What it would actually do in terms of the geometry is with that triple bond, it actually would be linear. So sometimes you'll see people kind of straighten it out when they draw it. Most people are okay if you leave it like that and draw it without the geometry, but sometimes you'll see it straighten out because, again, technically in that case with the triple bond there, that's going to be sp hybridized, which is linear, and it would be a more of a straight line. That's also why in a alkane type situation where you just have single bonds, each of these guys basically have 4 electron pairs and 4 bonds, and that basically is tetrahedral, which is why a lot of times in line structures, sometimes referred to as drawn in that zigzag shape, they each have basically tetrahedral geometry, which gives it that kind of up and down sort of shape. Any questions on that there? So then let's talk a little bit about functional groups in organic chemistry. Functional groups are really the part of the organic molecule that makes it a specific type of organic molecule. It is sort of the part of the molecule where pretty much everything occurs. It's kind of the important part of the molecule. And there are several different functional groups in terms of organic, and they represent different types of organic molecules. So really the first basic type are alkanes. And alkanes have really the functional group of the carbon-carbon single bond, although some people will say that's not really a functional group, but that's sort of how you can recognize it. It's really all carbon-carbon single bonds are a class of organic molecules, which are known as alkanes. Alkenes, ENE, have the carbon-carbon double bond, so at least 1 carbon-carbon double bond present. Alkynes have a carbon-carbon triple bond present. There's the alcohol, like we talked about there, which has an OH group. We also have ethers, and ethers have basically a carbon-oxygen-carbon sort of run in there. There are thiols, which is actually a sulfur-containing group, similar to the OH group there, but basically a sulfur instead of an oxygen. There are aldehydes. Aldehydes have the carbon-oxygen double bond, a carbonyl group with a hydrogen at the end. There's also ketones. Ketones have basically a 3-carbon run and in the middle you have that carbon-oxygen double bond, makes it a ketone. Blah, 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 blah. How about esters? Esters have a carbon-oxygen double bond to an oxygen, and then usually attached to a carbon is sort of your ester. It's actually made from a combination of a carboxylic acid and an alcohol coming together. Speaking of that, carboxylic acids we looked at a little bit a second ago. Carboxylic acids is a carbon-oxygen double bond to the OH. A lot of times in formulas, it's written like COOH. So that is basically what it represents, is that guy right there. And there's also some nitrogen-containing guys. There's amines, and amines are basically derivatives of ammonia, and they have basically an NH2, a nitrogen sort of containing group. And there's amides or amides, which looks like this as well. So each of these are really sort of the functional groups in organic chemistry, and each of them are named slightly different depending obviously on which functional group is present. The most important probably out of all of them, especially when you're starting organic chemistry and learning all the names and stuff like that, is actually the alkanes. Pretty much everything in organic chemistry in terms of names falls back to the alkanes. All these different functional groups, if you wanted to sort of name them properly, they really do all come back to those sort of first 10 alkanes or so in terms of how you name it. So most important to get those in your head first, because it does help with a lot of the naming part of it. Any questions on any of those there? Now, let's then talk about alkanes specifically and sort of what happens with alkanes and a little bit about alkanes. And we'll start with those guys first off. So alkanes are really your basic organic molecules. They are the carbon-carbon single bond, basically. And they have a general formula of CnH2n plus 2. And N is the number of carbons there are. So for example, if you had one carbon, 2 times 1 is 2 plus 2 means you have 4 hydrogens. And that is what is known as methane, ANE. If you had 2 carbons, 2 times 2 is 4 plus 2 would be 6. You would have 6 hydrogens. That is known as ethane. If you had 3 carbons, that would get you 8 hydrogens. That is known as propane. If you had 4 carbons, that's 10 hydrogens you would have. That is known as butane. 5 carbons will get you not 20, but 12 seems like a better number. Will be pentane. 6 carbons will get you 14 hydrogens is hexane. 7 carbons will get you 16 hydrogens is heptane. 8 carbons gets you 18 hydrogens is octane. And to finish out the first 10 here, C9H20 is nonane. And C10H22 is decane. So really these first 10 alkanes are really the basis of all the other functional groups, all the other organic molecules, and pretty much in most cases, how you go about naming these guys. These all have carbon-carbon single bonds. They all end in ANE, just like kind of the name of the group. So alkanes, ANE, that's how basically all these guys end. If you take an alkane like, say, our propane, and we drew it out, this is also sometimes referred to as a hydrocarbon because, frankly, it has just hydrogens and carbon. So this is a hydrocarbon. And this is also sometimes referred to as a saturated. So a saturated hydrocarbon what the word saturation means in this case is each of those carbons have the maximum number of hydrogens that it could have. So in this situation, because everybody is single bonded, we pretty much have the maximum number of hydrogens that is possible, and as was referred to as a saturated hydrocarbon. Now, one of the consequences of obviously carbon having to maintain the octet rule is when we make like a double bond, for example, we do have to do some work here with our hydrogen. So let's say we wanted to double bond the carbon on the right-hand side. And if we did that, we double bonded this carbon on the right-hand side, we would end up with something that looks like this. And in this particular case, a couple of things are different. First off, we had to sacrifice a couple of hydrogens, right? And the reason we had to sacrifice a couple of hydrogens is if we left those hydrogens there, that carbon or each of those carbons would actually have too many bonds. So in organic chemistry, pretty much every time you lay in like a double bond or you lay in a triple bond, every time you kind of add a bond between two carbons, you have to sacrifice basically two hydrogens, one on each of the carbons. Otherwise, you'll end up with too many bonds. And in this case, what happens is if we want to say make a triple bond at that carbon, we would look something like this. And now we had to actually sacrifice two more hydrogens, one at each of those carbons to allow that triple bond to go in there. So again, that we are not over the limit, if you will, in terms of electrons. Now, by making these double bonds and triple bonds, we actually have now made, we had an alkane up here, which is our single bond. This guy is now an alkene, ENE, which has our double bond. And this guy down here is now an alkyne because it has a triple bond that's happening. Now, when we look at this here, these two guys here, these are what are referred to as unsaturated hydrocarbons. And that is because it has at least one double bond or triple bond, which means because of that, you no longer have the maximum number of hydrogens that you could have. And they're referred to as being unsaturated. Now, in terms of how names work, just to kind of demonstrate with this pretty straightforward example here, this is 3 carbons, which is known as propane, ANE. This guy up here, which now came. By putting the double bond, it now becomes propene, ENE, just like an alkene. And putting in the triple bond, it now becomes propyne, YNE, just like our kind of group name. So everything's related to the alkane name. And really, as we'll talk about a little bit here, it is related to really how many carbons there are. So when you go to name something, you're always looking for the longest number of carbons or the longest continuous carbon chain. That basically dictates how the name should be. And a lot of times the longest continuous carbon chain will match up with one of these 10 sort of names. And that's really the base of your name. And depending on the functional group that's present, then you do some little bit of alteration as to how to kind of finish out the name. Any questions on that there? Now, when we look at carbons, we could also classify carbons as being either a primary carbon, a secondary carbon, or a tertiary carbon. And if we look at that, our carbons can be primary, secondary, or tertiary. And it's a primary carbon, secondary, or tertiary carbon. And it really is a couple ways you could sort of figure out what is a primary, secondary, or tertiary. I personally am fond of the easier way of doing it. So let's just talk about that way, I think. But if we wanted to, for example, classify that carbon right there, all we have to do is simply figure out how many carbons are directly attached to it. So in this case, there's just one carbon directly attached to it, which would make this a primary carbon. Some people will tell you to count the hydrogens. So if you got 3 hydrogens, it's primary, but it seems to make more sense just to count the carbons, because it's however many carbons you have is basically what the classification is. If you took a carbon that looks maybe something like this, I won't draw them all out here. We'll do this and something like this. So if we look at this carbon right here, it is attached to that carbon. It is also attached to that carbon, and that would be 2, which would mean that that would be a secondary carbon. You could also see it has 2 hydrogens, which is another way you can look at it. And if we had like a tertiary carbon, it would be directly attached to 3 carbons in this case. So this guy directly attached to 1, 2, and 3 carbons would make that a tertiary carbon. So primary, secondary, and tertiary is a very much a way we classify carbons. It also happens when you are, for example, classifying alcohols. You could have a primary alcohol, which basically has 1 carbon attached to the carbon that has the OH group. You could have a secondary alcohol or a tertiary alcohol as well. So we do see this sort of classification happen in a lot of organic groups, including alcohols. Also, amines are also classified that way, amides as well. So there's a lot of sort of classification. It also plays a role in terms of groups, for example, that are attached in an organic molecule. So in an organic molecule, we can actually have a couple of different ways that that guy is sort of put together. We could have what is sometimes referred to as a straight chain, something that looks something like this, where basically all of our carbons and everybody runs kind of in a straight line. So this is sometimes referred to as a straight chain. We could also have, for example, a branch chain where, you know, maybe I'll just draw it this way here, I think. Where there's kind of a main part of it, but then there is some stuff kind of hanging off of it. And much like a tree, you could have many things kind of coming off in some different directions. Unlike the guy on the left there, where everything basically just runs through. So this is what is sometimes referred to as a branch chain. You could also have ring type of structures where basically the alkanes, for example, close up on each other and make a lot of times they're drawn as line structures, geometrical sort of shapes, if you will. Each of those would be a carbon, like CH2 to CH2 to CH2. And again, it closes up and makes sort of a ring shape. So that's very common. I guess in terms of what I should have added back here as well is aromatic is another functional group. And aromatic has what is referred to as the benzene ring. And so that's the benzene ring. It's basically a 6-carbon ring that has 3 double bonds in it. You could also do a resonance structure where those double bonds move around. And sometimes in some books, they will draw the benzene with like a little circle in the middle to indicate that those double bond electrons are basically moving around. So anything that has a benzene ring in it is considered an aromatic sort of classification. And that's like C6H6. There's a hydrogen at each of those carbons. Each of these points here are obviously carbons, and each of those guys would have 1 hydrogen basically attached in each of those guys. So aromatic, again, another sort of functional group, and that brings up a lot of different types of names. So getting back to sort of this idea of groups and sort of the main chain, when we look for the longest carbon chain, when we're going to name something, anything that's not part of it is considered a group. And sometimes these groups are considered what is referred to as an alkyl group. And those are carbon-containing groups. And they also are based upon the first 10 alkane names. So for example, the guy is circled here, the CH3 group. That CH3 group has one carbon, which means it is based off of methane. And if you remember, methane is one carbon, but 4 hydrogens. Right? So that's methane. Now, if I wanted to use methane and attach it into that main group and just kind of attach it there, ignore this guy being there for now. If I did that, the problem would be that that guy would then have 5 bonds, right? And carbon would have too many electrons. So we cannot attach methane the way it is. We actually need to drop off a hydrogen to give it an attachment like it is in this compound here, where it's missing 1 hydrogen, and that allows it to bond into the main chain and still maintain the proper number of electrons without going over to 8. Now, it is actually named based off of methane. We actually dropped the last part of methane, and this is what is known as a methyl group. And methyl, because this is an alkyl YL group, so that is what we do with the name there. It goes from methane to a methyl group. So pretty much everybody on those first 10 alkanes can basically be a group that's attached and is named sometimes as a group. They all are missing basically 1 hydrogen. And by missing 1 hydrogen, what that allows it to do is be able to have a place where it can connect in and not be over too many bonds. So for example, you know, we could take any one of these guys here. Some of this here. So if we took a ethane, right here, this guy, and again here our ethane would look like this. And if we took off one of the hydrogens, it has 2 carbons based off of ethane, this would then become an ethyl group. If we did our propane, and again took off one of the N hydrogens to allow it to connect in, that has 3 carbons, which is based off of propane. This would then be a propyl group. Now, it does matter in the sense of what type of hydrogen you take off. And what I mean by that is basically what type of carbon it came from. Is it a primary carbon, secondary carbon, or tertiary carbon that it came off of? And if we look at propane, for example, the one I just drew here, we basically took the hydrogen off of a primary carbon. It's basically at the end. If you took it off the guy at the other end, which is also a primary, you can have the same sort of group. But if I took the hydrogen off of this carbon here, which is actually a secondary carbon, we actually get a different type of group that occurs, because the connectivity now will be right here at our secondary carbon. And this actually has a special name, which is known as isopropyl group. Propyl, because it has 3 carbons. Iso pretty much means anytime you have a group that has a CH3 kind of on both ends like that, it kind of makes what is known as an isopropyl group. You could also do that with butane. You could take off the hydrogen at the end and you'll have a butyl group. You could take off a hydrogen from the secondary carbon in butane, and you will have what is referred to as sec-butyl for secondary butyl, the secondary carbon, the hydrogen that came off of it. You could also have T-butyl, which means the hydrogen comes off of the tertiary butyl, or tertiary carbon that is there as well. So there are some of these sort of historical names that are used for groups. Isopropyl is a very common one. Sec-butyl or T-butyl is also a very common sort of guides as well. Any questions on that there? So that brings us to talking a little bit about, I think, isomers. And we talked a little bit about isomers, I think, when we're talking about transition metals, but isomers are basically the same molecular formula. But you got some type of different connectivity, So for example, if I took this guy here, and then maybe I take this guy here. Maybe I take this. Okay, so if I look at all these guys here, I want to determine whether or not, say, these are isomers of each other, or they're not isomers of each other. So really should count up what we got going on in terms of carbons and hydrogens in each of these. And if I take the first one here, that guy's got 4 carbons, which also means if we count up our hydrogens there, we should have 10 hydrogens. If I count this guy here on the right, I got 4 carbons. And I got 3, 6, 9, and 1 hydrogen in the middle, which would be 10. If I count this guy, 1, 2, 3, 4 carbons and 10 hydrogens. So they all do have the same formula. They all maybe look a little different, but we need to determine, are these guys really different or not? So the best way to determine whether or not you sort of have an isomer is to frankly name everything. And obviously, if you do it correctly, that's an important part of it. If you name something and it ends up with 2 different names, then you really did probably draw an isomer. If you name something and ends up with the same name, even though it may look different, it is probably the same compound and you really didn't draw a second isomer. So let's name this. And basically, to name something, what we're looking for is the longest continuous carbon chain. It doesn't have to be the straightest. It could go straight, it could go up, it could go over, it could go straight, it could go down. You could start up on top and kind of curve over to the right and come down. The only thing that you cannot do is pretty much backtrack. So you got to start in one direction and keep going till you kind of hit a wall. You can't go any further in terms of carbons. You can't backtrack. So with that in mind, if I just run straight across here, obviously 1, 2, 3, and 4 carbons there would be the longest continuous carbon chain. There's absolutely nothing else attached in that molecule except for hydrogens, which are not considered groups here. So that would just be 4 carbons, which is butane. So that's basically what we started with, is butane in this case. When I look at the guy to the right, I want to basically count the longest continuous carbon chain on this guy. And if I start straight across, 1, 2, and 3 only. We also could go straight and then go up, which would also give us 3. We could also go on the right-hand side, kind of straight and then up. That would also give us 3. And that happens a lot in organic chemistry. There could be multiple ways in which maybe you end up with the same number of carbons as the longest continuous carbon chain. But you should always check it, because sometimes they may be hidden, and sometimes people get into a thing where they just take the straightest one in front of them. But again, it could start up and kind of go over to the right. So you want to check everything. In this particular case, we have the longest continuous carbon chain is 3. That means that this guy right here is not part of the longest continuous carbon chain, and that would be considered a group in this case. So we got the guy in yellow, which is our longest carbon chain. We got this guy, which is a group. So if we were to name this, really the basis of our name will come from our longest continuous carbon chain, which is only 3 carbons, and that would be propane, right? Is 3 carbons. This being a group that has 1 carbon is based off of methane, and because it's an alkyl group, that would be a methyl group. The YL, again, is missing that hydrogen to allow it to connect in. The last thing that we want to do kind of when we name is, basically names are all about location, location, location. You're basically telling everybody where you can find everything. And in this particular case, we want to number the longest continuous carbon chain. And the longest continuous carbon chain is numbered by 1 of 2 ways, kind of either left to right, or really you could go right to left. And in the case of alkanes, what we're looking to do is number whichever way will give the actual groups the smallest number. So in this particular case, it actually doesn't matter. You can go left to right or right to left. That methyl group is sitting at carbon number 2 no matter which way that you go. So it doesn't really matter. So we will add a 2 to it. And by the way, we do a number and then we put a dash between a number and a letter. So it'd be 2-methyl. And that's pretty much our entire name here. We put it together, 2-methyl propane. So although it does have the exact same molecular formula, C4H10, it has a different name, a different connectivity. These two guys here are isomers of each other, right? Any questions on that there? Now, what about the guy on the bottom? If we look at the guy on the bottom and we take that same path to name it, we're going to go with the longest carbon chain. So that's going to be 1, 2, coming down is 3, coming over is 4, and there's nothing else there, right? So that is 4 carbons, which means that this guy is also known as butane, yeah? So this guy here and this guy here, they're the same thing. They're just drawn differently. And that's very commonly what happens when people try to draw isomers. They go, I'm just going to draw the end up and the other end down, and it looks different, but it's really the same molecule in this case. So this guy down here would not be another isomer. It's really the same thing as butane in this case. And that's really a good way, as I mentioned, to sort of check yourself is, you know, if you draw it and you get multiple names, then, you know, you probably did draw some isomers, but even if you draw it and it looks different, and you get the same name, it probably is the same thing. Any questions on isomers there? So since we sort of talked about there how to go about naming, let's talk officially about how to name things. So when we name things in organic chemistry, a lot of times we follow what is referred to as the IUPAC way of naming, and that's the International Union of Pure and Applied Chemistry. Those are the 3 guys that tell you how you're supposed to name everything in chemistry. You could thank them. But they have all the rules of how you go about naming things. And when we're doing alkanes specifically, these are pretty much the steps that you follow. And for the most part, even outside of alkanes, other functional groups, you follow a very similar path. It pretty much always starts with finding the longest carbon chain. And again, that is what we were just talking about. It could be straight, could go up and over. Again, you just can't backtrack. When you find that longest continuous carbon chain, that will most likely match a alkane, one of those first 10 alkanes, and that really will be the base of your name. Once you do that, you want to ID the groups that are attached. And as we talked about, if it is a carbon-based group, it will have that YL ending. So again, like SCH3 would be a methyl group, a CH2, CH3, which is 2 carbons, would be an ethyl group. We had some of those special ones like CH3, CH3, which is isopropyl. Also, you know, you can have something like a halogen. It's very common to come across. So if you have a fluorine, that's a fluoral group. If you have a bromine, that is a bromol group. If you have a Cl, that's a chloral group. If you have an I, that's an iodo group. So those are how sort of halogens are named when they find their way onto an organic compound, which happens a lot. A lot of reactions involve halogens, like adding halogens to them. So they do end up on there a lot. Once you have your longest continuous carbon chain, once you figure out what things are groups, the next thing you want to do is number the longest continuous carbon chain. And in the case of alkanes, what takes the priority is actually the groups. So as we did in that last one, you want to number whichever way will give the groups the smallest number. So it's always the smallest number in organic chemistry is what you're looking at. So you want to number whichever way gives the groups the smallest numbers. Now, that part of it does change as you move away from alkanes and you get into things that have some other functional groups like double bonds, triple bonds, OH groups. And most things past our alkanes, sort of the priority in terms of numbering is actually the functional group. So if you have like an OH, you would want a number whichever way gives the OH the smallest number. If you had like a double bond, you would want a number whichever way gives the double bond a smallest number. But with alkanes, since the functional group is the carbon-carbon single bond, the actual groups that are attached to it gets the priority. But that does move as you sort of get to other organic molecules. Once you've done that, we're going to put all of our groups in alphabetical order. Regardless of prefix and also regardless of number. And what I mean by that is you could have alphabetically something that's B before M, but the B has a larger number than the M. We can still go alphabetical regardless of the number. Also, in terms of these groups, we sometimes will use prefixes if we have multiple of the same group in the compound. Doesn't necessarily have to be on the same carbon, but if you have multiple of the same group in the same compound, we use things like di for 2, tri for 3, tetra for 4 for our groups. And lastly, just some of the stuff that we mentioned here. Every time you take a number to a letter, or you go from a letter to a number, we put a dash between. We don't circle them, but we put a dash between them. And in some cases, you may actually end up with 2 numbers in a row. And if you have 2 numbers in a row, we put a comma between the 2 numbers is how we go about sort of naming those guys. So for example, if you had 2 methyl groups, you would call it dimethyl. And again, it doesn't have to be on the same carbon. It could be just anywhere in the compound, 2 of the same groups. You would include those prefixes. Any questions on that there? All right, so why don't you try a couple of stuff we've been talking about here. Let's go with, we'll do D5H12. All right, so why don't you name each of these and then also decide, are they all isomers of each other? So let me do this. I'll just draw the condensed formula, I think. Let me do this. Let me do this. And let me do all right, so give the proper name for each of those and decide, are they all isomers of each other? Okay, let's take a look and see. So we'll start here in the first one. We're going for longest carbon chain, which just looks straight across there. So that's going to be 5 carbons. Nothing else is attached really except for hydrogens. So that's going to be our friend pentane is our name there. We go to guy to the right, looking for the longest continuous carbon chain. Again, we could just go straight here, 1, 2, 3, 4. By the way, if you went straight and then up, that's only 3. But if you started at the other end, went straight and went up, that's 4 as well. So again, it really doesn't matter which way you choose the longest continuous carbon chain. I personally think just taking the straight one is probably the easiest to see. Then you can box out your group that would be attached right there. So starting with our longest carbon chain, that's going to give us really the base of our name, which is 4 carbons. So that's our friend butane. This is our 1 carbon group. Since it's a group and not the alkane, we put the YL at the end of it, and that's going to be our methyl group. Remember that we do need to give the location of where that group is. So if we went left to right, that would be carbon 1, 2, 3, and 4. we went right to left, that would be 1, 2, 3, and 4. And in this case, going left to right, that guy's at carbon number 2. Going right to left, it is at carbon number 3. And it is as simple as 2 is less than 3. So that is the way that we would want to go. So we would want a number in this direction because it gives the group the smaller number. That means that that is going to be a 2-methyl. So putting all that together gets us a 2-methyl and butane. Has still the 5 carbons and 12 hydrogens. Has different names, different connectivity. These two right here are isomers of each other, right? Because they are different, but has the same number of elements of each of those things. Question on that so far. Going to the guy on the bottom, longest carbon chain. No matter which way you go, it's going to be 3. We could go 3 that way. We obviously could get 3 going that way. You could get 3 going that way. By the way, you could get 3 just going straight down as well if you want. All ways there, looks like 3 is a winner in terms of the longest continuous carbon chain. That means that we actually, in this case, have a couple of groups hanging off. We got this guy here, that's a group, and this guy here, that is a group. Our longest continuous carbon chain in this case is actually only 3, which means the base of the name is going to be propane because there's 3. That is a methyl group, which is a 1-carbon group. Same thing down here. That is a methyl group because it's a 1-carbon group. That is 2 of the same groups in this compound. That means we use a prefix here, and that's a dimethyl situation happening here. Now we need to get the location of those. You can probably just see it no matter which way you go. Those groups are going to end up at carbon number 2. So it doesn't really matter in this case. So putting that together, this would be 2, 2. You do have to get the location of both of those groups, even if they're on the same carbon. And even if they're on different carbons, you need to give the location. We then would do a dash between the number and the letter. So that is 2, 2 dimethyl, finishing it out here with propane. We count up our carbons and hydrogens here. That is 5 carbons and 12 hydrogens. That means that this guy as well would be an isomer as well as those 3. So those 3 are isomers of each other. We have different names, we have different connectivity, but we still have the same number of each of those. That leaves the last one here on the right. And if we do that, we got 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. So even though it may look different, that is 5 carbons. There's nothing else attached but hydrogens. This is still pentane, which means this is not an isomer. It's just this guy drawn differently. Yeah, so that would not be an isomer in that particular case. Any questions on any of those there? All right, we're laid up for now.